everyone for joining us this morning. It's my pleasure to host Peter Quell for his talk today. I am president of Model Risk Managers International Association, and this kind of educational talk is one of the things we like doing most. We are an organization focused on advocating for best practices in obviously model risk management, but from a perspective of practitioners. So trying to seek a balance between regulatory requirements and the needs of the business to promote best practices. So Peter Quell is a board member of MRMIA, and he is the head of portfolio analytics team for market and credit risk in the risk controlling unit of DZ Bank in Frankfurt. He's responsible for the methodological aspects of internal risk models, economic capital, and model risk. Prior to joining DZ Bank, Peter was manager at Define GmbH, where he dealt with various aspects of risk management systems in the banking industry. He holds an MSc in mathematical finance from Oxford University and a PhD in mathematics. And so, Peter, and you're also on the editorial board of the Journal of Risk Model Validation. So Peter, thank you for taking the time to present to us today. I look forward to hearing your talk, and I'll turn it over to you.
Okay, thank you, Joe, for the kind introduction, and welcome everyone to this session on one aspect of artificial intelligence within model risk or model risk validation. I guess it was around 2 years ago when we started our journey in exploring how to employ machine learning or artificial intelligence, if you like, for the purpose of risk modeling or risk model validation. And if you like, you can also download a few results of this endeavor from our website, MRMIA.org. We issued a white paper on the use of machine learning in risk modeling about beginning of 2021. And we also had a few practitioners workshops on this, where you can also find recordings on our website. Especially if you're interested in topics like fairness and explainability in AI. That was one of the topics from our last practitioners workshop in the summer 2022. Then I invite you to visit our website. So today I want to continue exploring the way how you can use machine learning within risk modeling. And this is my plan for today. You see that we are going to tackle or try to tackle the application in market risk, because previously we focused much on credit risk area, and I want to see how far we can push the button or how the pedal to the metal in order to also employ machine learning within market risk. You see, we are encountering a good old companion from the early ages of information processing, the Kalman filter for tracking under noisy observations. Maybe one or two of our attendees have already encountered this Kalman filter. So I will try to see how this can be thought of as some sort of ancient AI and how it can be used. But also I'm trying to focus a little bit more on the general approach for time series analysis using machine learning or AI. Having said that, let me just give you a brief overview on my perspectives. And by the way, I've forgotten to tell you this. Of course, everything I'm telling you here is my very own subjective view on the landscape, on the methods here. So please bear with me. All errors are mine, and it's not representative of MRMIA or DZ Bank. But nevertheless, I guess we have some substantial material to talk about today. So In a classical setting, you have more or less three big applications of AI within the financial industry. One is credit scoring, where you try to employ or exploit data about people applying for a loan. May it be unstructured data like contributions to a blog or to some social platform, social media platform. It can also be the data coming from accounts, previous accounts of these people and other financial institutions. And the typical techniques we are using in these areas are the more or less all-purpose working horse of artificial intelligence, the neural networks. You can also use some easier to grasp maybe techniques like decision trees, the good old support vector machines, and as I said, alternate data like natural language processing and so on. This way of using methods from machine learning or AI in the credit scoring has a quite good tradition. And if you're interested in these areas, maybe I can refer you to the white paper that I previously mentioned on the MRMIA website. The next good old friend in the application of machine learning to credit or to risk in general is the anti-money laundering and fraud detection area, where techniques like k-means or clustering, support vector machines, or naive Bayes methods are heavily employed and have also quite good tradition, and people know the weaknesses and strengths of these methods. And this is, as I said, not what I'm going to talk about today. Today, I want to focus on the third area. This is more or less the dynamic part, which is more related to time series analysis. You see there some techniques like the Kalman filter, which I'm going to talk about in a few minutes, and also the long short-term memory methods. So sorry for the mispronunciation, is LSTM, long short-term memory, and also the hidden Markov models. And as I said, there is a quite subtle distinction between these three areas, or the two previous areas and the dynamic area here. And one thing I'd like you to take away from this presentation is that, in my view, the capturing or the application of machine learning is quite well established in the static area, but maybe there are some subtle issues in the dynamic area. So where are the perspectives? Of course, machine learning in risk modeling can be founded or can be based on large amounts of data. There's lots of financial data running around just to be ready to grasp for us. Machine learning can also be used to construct benchmark models. And here you see I'm a little bit careful, since I know that risk modeling is a quite heavily regulated area. Of course, a lot of risk models are only there for regulatory purposes. And since the regulators are maybe not the most early adopters of AI or machine learning, therefore I'm talking here about slow pace into using artificial intelligence in risk modeling, starting maybe with the construction of benchmark models to challenge already existing risk models, maybe for pillar 1 or pillar 2 purposes in various areas like market risk or credit risk and so on. Of course, I know that in the rating or credit risk area, we already have some quite successful applications of AI also in a regulatory risk framework. But as I said, today I'm thinking more or less about the market risk or trading book area, and there the use of machine learning for risk purposes or risk modeling purposes is not so widespread. And also you can use machine learning algorithms, of course, in the automated model validation arena. Yeah, that's maybe a good description of the perspectives, but there are also some problems. which may prevent us from being too far at the moment. So one is insufficient labeling of data. We have tons of data, but the way it is labeled or being prepared for the processing by our AI machines or AI machine learning applications is quite limited. We have model risks, of course, in the machine learning, and I'm pronouncing or try to emphasize this because some people think that machine learning is just based on data alone. There are no theories. There's no theory behind this. There are no mathematical models or mathematical theories. There is no economic theory behind that. It's just people let data speak for itself. But even then, if this would be true, even then there would be model risks because people are cleaning the data, are selecting data. There are biases in data and so on. So there's also model risk in machine learning. One of these model risks is the black box issue of overfitting. And this is one of the key concepts I'm trying to explore in the later slides. Also the last point may be quite relevant. We are talking about sometimes in risk modeling, we are talking about very rare events. We are talking about quantile estimation and stuff like that. So maybe the corresponding data, which is really relevant in these areas where you're trying to measure risk, is also quite limited. So we have lots of data, but maybe it's still not enough. For example, to capture real tail events or black swans or so. So there's, I guess, a philosophical component to this, also related to Nassim Taleb's concept of black swans or anti-fragility. But there are also some quite immediate technical issues to this. So, as I already said, there are some general issues which I commented on in the last slide. But to make this very clear, let me just focus on these 5 issues that are especially relevant also for our undertaking of seeing how far AI and machine learning could be employed within market risk. One aspect of financial markets is they are unstable. There's a time varying volatility. It's called heteroscedasticity. Everything changes from now and then, and therefore you need to account for population drift or the changes within the data environment that you're looking at. So this is a very clear must-have within the time series analysis algorithms we are using. The algorithm needs to be in a position to cope with population drift and needs to be quite robust in changing environments. The bias issue, I already commented on the bias in the credit risk applications. This also relates to fairness issues, for example, in credit approval processes. And bias in data is then, of course, replicated in biases within the results of these, or the results of the outputs of those techniques. The brittleness issue is also quite relevant when we talk about overfitting and market risk. It's a concept you may have come across when people were trying to use machine learning for face recognition or image recognition. There are quite nice examples when you have, for example, the picture of a cat, and you brittle it a little bit or make it a little bit more fuzzy, and then suddenly some AI algorithm detects an elephant or a snake or whatsoever in this picture, where a human would definitely see this is just a fuzzy cat or something like this. So these apparently good performances, which quickly get worse under small variations of environment, is called brittleness. This is also somehow meaningful for the market risk area, but I just mentioned it here for the sake of completeness. Also, the p-hacking is nothing new under the sun, since p-hacking is also present in statistics. It was or is still a big problem within regression analysis when people are only reporting those regressions that work or that conform to their opinions, and they just do data massaging until we have the corresponding p-values. This is also present within machine learning. It's then not called p-hacking, but you see, whenever you prepare data, you have a training data set and a performance data set, there are plenty of ways of falling into this trap of p-hacking transferred to machine learning. The most important point, and therefore it's colored in red here, is the signal to noise issue and detection of false patterns issue related to overfitting. And one of the key points I try to convey today is that financial data is inherently noisy. And it is, of course, interesting to separate the signal from the noise within financial data. But if you are not recognizing the role of noise and you're just learning noise patterns, then this is not a big progress. On the contrary, it's quite dangerous if you think that you see patterns in noise where you just have white noise, for example, where there are by definition no real patterns are present. You see those patterns and you think you can trade on them. So this is therefore a very, very important topic and very important exercise to separate signal from noise. And I'm not claiming that I will solve this issue once and forever within the next 20 minutes. But nevertheless, I try to tell you some of my perspectives on these issues. And just bear in mind the quote from Lotfi Sadeh, one of the founders of fuzzy logic, that whenever you have a lot of complexity, precise statements lose meaning and meaningful statements lose precision. By the way, the 4 pictures on the slide somehow relate to the distinction between noise and bias. Maybe you have read Danny Kahneman's book on noise, which came out, I think, last year or the year before. You see the first on the left is noisy. The third is also noisy. The third may be a little bit more centered without bias. Also, the fourth is centered with low noise and small bias. And this is more or less the distinction between noise and bias. You know, if those circles wouldn't be there, you just if you just have a look at the clouds of these points, then the first and the third are distinctive from the second and the fourth, and the first and the third would then count as high noise clouds, and the other ones would be the low noise clouds. But bias would then, of course, be a different story. We're not caring about bias today. We're caring about noise and the signal. So what about the Kalman filter? I call this some sort of ancient AI. Let's see if this really counts as an artificial intelligence or machine learning aspect or technique. What is the Kalman filter all about? It's tracking something under noisy observations. And of course, the Kalman filter was invented in military areas or radar technology. But it could also be transferred almost one-to-one to financial time series. As I said, the financial time series may be data from non-stable environments, from time-changing environments. You can just think about, for example, a mean of a stochastic process of something that wanders around, and you have noisy observations of this mean, and this is then the stochastic process. So it's not something like a stationary process, of course, since this would then have to be something with a constant mean. The mean is wandering around, and over this mean you have some noise, and the dark line here, or the dark trace, this track has is then the sample, and the gray area would then also be some area where the time series could also have been with a certain probability. So the exact position, the hidden state, is not known. We have a noisy observation, and the question is, how can we make optimal use of that data? And of course, there are different situations. I mean, it's almost trivial to track the signal under the graph on top, the large signal to noise ratio graph. Since the signal is large, the noise is considerably small. It's a quite easy task. The task may be a little bit more difficult if you have a small signal to noise ratio, and if you're interested in aspects like these. A colleague of mine, Christian Meyer, and myself have produced or published a book on risk model validation, which was in its third edition in 2020, and there we try to tackle a little bit this issue of using Kalman filter for the benefit of market risk modeling. But of course, now we are 3 years later, and we have developed new techniques, and this presentation is also about the developments since then. How can you build, and now we are getting a little bit more technical, how can you build a toy model to explain those main features? And just to some sort of spoiler alert, of course, I'm not presenting anything very new under the sun. I mean, what I'm showing you here is a, so to say, a noisy random walk. This is a very classical object of considerations within statistics or stochastics. Or I guess already in the 60s, we had people publishing on this. But nevertheless, it's a toy model which highlights the main issues I want to focus on. So you have a hidden component, and in this case, I have denoted this as mu, so to signal this is some sort of mean value. And the P&L, which should stand then for profit and loss maybe, is just a noisy observation of this mean. And what you really want to do is, since you don't have the mu, because this is the hidden state, you only have the P&L, then you need some sort of estimator, this I will call M, and just based on the observations PL, you have some sort of online estimator MN, which is just after every observation is updating the estimation M n+1 just based on the new information, which is contained in PLN+1. And you have maybe seen this if you are from the Marquis area. This is more or less also the foundation of all those exponentially weighted moving average algorithms, or the risk matrix algorithms. And the only thing that is still to be determined is the lambda. And there are certain ways of doing this. I don't want to go into technical details. What I want to show you is how can we apply this to maybe a more interesting time series. Here, for example, the US dollar euro time series containing around 8 years of data. I guess these 8-year time span starts in 2012 and ends in 2020 when we published the book. But I guess the main features are really present here in this graph. You see some sort of time varying volatility, some sort of heteroscedasticity. You see maybe with some stretch of imagination, you see those fat tails in the return time series. And these aspects that I mentioned, the fat-tailedness of the conditional or unconditional distribution and the time varying volatility, together with some other aspects, are called stylized facts, because these are observations which are similar across different markets. So it's not only restricted to foreign exchange, it could also be detected within equity returns, or maybe in interest rates or commodity prices. Observations which are similar across markets, instruments, and also time periods. And the question is, in this case, what is the signal and where is the noise? So the signal, of course, for risk management purposes, the signal we are focusing on would then be some measure, some deviation measure for volatility. It doesn't have to be the variance. It could also be something like the mean average deviation, which is more or less just a moment of order one, or the variance. I mean, we are quite flexible in this case, but nevertheless, we are focusing on deviations. And the standard way to proceed in this case would then, of course, be here in a short stretch of that time series. If, for example, we are here where we have these two arrows, maybe you have some sort of measure for the variance up to this point in time. Then you have the new information, which is just this return, this negative return. And the question is how to compute the new variance. It's, of course, this convex combination of the old variance and the new information. The variance is, in this case, just a second moment of the P&L, and we are not weighing it in an equal fashion, but we have some sort of exponentially weighted moving average approach here. So this is the signal, and where's the noise? Of course, the noise is then the conditioning of the P&L at time n+1 on the previously measured standard deviation, the sigma n. So that is not a typo. So we have n+1 for the P&L and the n for the sigma in order to represent the state of knowledge. So we are trying to make a risk forecast or risk, I wouldn't call it prediction, but a risk estimation or forecast for the day n+1, but based on the information up to time n. And this conditioning will then deliver some sort of noise component, which would then naturally lead to some sort of risk model where we just rescale the corresponding volatility based on our most recent information, and scale this with this noise component. And this would then be a more up-to-date description of the process for which we are trying to make some risk forecast or some quantile estimation. Of course, this needs some sort of remarks. Of course, if the risk measurement has a severe problem with tail estimation, which maybe all risk estimates have, then this is of course not the solution. So this is not a solution for all questions related to black swans or tail risk estimates. That's clear. This is a solution for the problem of time varying volatility. So if we have time varying volatility and we consider volatility or variance or standard deviation or in general a deviation measure as the signal, and then we could then interpret this procedure as a separation of signal and noise, at least on a very simple level. Of course, there are maybe much more sophisticated methods of trying to accomplish this separation of signal and noise, but for a starter, I guess this is a quite good approach. Why do I know this is a quite good approach? Because we have at DZ Bank, where I'm responsible for methodological aspects for market risk, we have constructed a challenger model for our champion model, which is just a plain historical simulation. And we call this challenger model, the adaptive market risk model. And this is more or less some sort of method that is just built on top of the existing historical simulation. We do not have to implement, or we didn't have to implement a lot of new code. We just used the scenarios coming out of the historical simulation and modified them in order to come up with the performance of the risk model depicted on top compared to the historical simulation on the bottom. So you see that this adaptive market risk model produces, of course, more volatile risk numbers, but it is much more adapted to the current level of volatility than the plain historical simulation. You see the historical simulation, the plain historical simulation, or the equally weighted historical simulation takes a lot of time in order to adapt to increasing volatilities that will produce a lot of outliers, backtest outliers, which then enter via this surcharge factor into your market risk capitalization. And it also needs a lot of time in order to reduce volatility once times are a little bit calmer. And this also consumes a lot of regulatory capital. So you see that the adaptation to increasing and decreasing volatilities is, of course, much better. And also standard backtest results. So not only counting outliers, but also backtest results, considering the complete P&L distribution, will be much more favorable with the adaptive market risk model than with the historical simulation. And as I said, one nice selling point would also be that this adaptive market risk model can be easily built on top of an existing historical simulation. So we have done this, and in the book I mentioned, we also describe how we have implemented it and which tests we have performed, and it is quite an interesting challenger model. And we are using it for the sake of validation, and we demonstrate to the regulator with this adaptive market risk model that we are not underestimating or overestimating with the historical simulation, because it happens that the historical simulation together with the backtest outlier factors is more or less comparable to the adaptive market risk model. But the adaptive market risk model is correct for the right reasons, where the historical simulation may just be one special point in time where the equal capital consumptions may just be a coincidence. Okay, so what about? I said that the Kalman filter is around for half a century now. What are more general or more contemporary approaches to this? One line of thought is related to the state space models, for which Kalman filter is obviously a simple representation, and also hidden Markov models could be interpreted in this fashion. These simple state space models are fast. They almost always share some sort of online capability of online learning, sequential characteristic, but sometimes they are quite restrictive. You know, whenever you do the math, there's sometimes some Bayesian flavor in this. Then you need certain kinds of distributional assumptions in order to make the calculations feasible. Or you have a very complicated machinery of maybe Markov chain Monte Carlo methods, which then are quite time consuming. Of course, you can get over those restrictions just by brute force, but usually people are restricting their analysis to the easy models. Then, of course, there's this recurrent neural network or long short-term memory line of thought. It's well established, for example, in speech recognition. There are a lot of free libraries, but at least to my knowledge, there are quite some problems related to overfitting. I know that there are debates between people favoring long short-term memory or RNNs and people who do not like them too much. And they always argue about the role of overfitting within LSTM, since overfitting is not so a big problem within speech recognition, maybe, but it's a big problem within financial markets time series data. Maybe in speech recognition, usually if the signal to noise ratio is very small, then maybe these algorithms just give up and say there is no signal. But within financial time series, we inherently have low signal to noise ratios, and therefore we cannot just raise the white flag and say we cannot do anything. We need to perform on these low signal to noise ratio time series, and then we have to see how far we can get with our methods. And one good candidate in this area, now the so-called particle methods, they are more or less natural extension or generalization of the Kalman filter. They have quite good performance. They are not so restrictive. They are from the outset quite general methods. But at least to my knowledge, there are currently only a few good libraries where you just can download the corresponding algorithms and start exploring the potential of these methods applied to financial markets time series. And just as a side note, also for Kalman filter and the particle methods, there are some extensions to the nonlinear case, but maybe we shouldn't start with the more difficult areas. Maybe we could, in step one, just restrict ourselves to the linear case. So I have done a lot of analysis with the Kalman filter or the simple state space models. I'm just starting to explore the particle methods, but if somebody of you has some repository of good libraries or experiences on the good side or on the bad side, I would be very eager to learn about that. And also, of course, if people from the RNN or LSTM line of thought could give me their insights, that would also be very welcome. Okay, so this is more or less as I said, my personal perspective in these kind of methods, and I'm also eager to learn what you think about this. Okay, so let me just conclude before we get to the Q&A session. I would say that risk modeling is a little bit different from maybe standard applications of AI, but as I said, also in credit risk, AI was very successfully used in order to improve existing algorithms. And I know, of course, sometimes the distinction between classical statistics and up-to-date AI is sometimes a little bit tricky. But I wouldn't go into these philosophical details for the moment. As I said, within time series analysis, for financial time series at least, we have small signal to noise ratios. And this is then always an area where some AI techniques may fall for this aspect of overfitting. We also have environments that are not constant. Time varying volatilities is maybe the best representative of this of these characteristics. Sometimes we have very small amounts of data. Our historical simulation, for example, at DZ Bank is using just 250 trading days of data for the current value at risk, and this is for machine learning method. It's I guess the time series is too small and too noisy. There are ML methods or machine learning methods to cope with time series data, but as I said, we need to explore the potential and also the dangers related to overfitting, to brittleness, and also to population drift. But I guess people are working on this, and maybe not the first one who has found out that there are some dangers, but I haven't seen something that really satisfies my needs in order to use this in front of a regulator to tell them now we are ready to employ machine learning or AI within the market risk area as a champion model. There are interpreted alternatives, and this is also one aspect that we covered in our last practice summit. The concept of interpretability is also quite relevant once you use these techniques for regulatory purposes. The Kalman filter is easy to interpret, and also the particle methods would also be easy to interpret. Yeah, so this is more or less everything I wanted to say. Yeah, back to you, Joe.
Thank you, Peter. Thanks for taking us through that. I have an immediate question about when you talk about recurrent neural networks and some of the methods, and I think this gets to what you're talking about, but how have you seen people deal with economic cycles? Because often the data they're modeling is a short bit of history, but when you look back far enough, you get major economic cycle events. And I saw that those kind of events in your Kalman filter data. So yeah, what do you think?
The most immediate answer I would have for this is, of course, they're just using very long time series. Sometimes in these long recurrent networks or long short-term memory methods, there are parameters in order to, so to say, separate effects on a large time scales from effects on a small time scale. But also there you need to have some, let's say, domain knowledge. I mean, I wouldn't be so pushy in order to say that we need some sort of Austrian business cycle view on these areas where you have, let's say, cycles of 5, 7, or 11 years or whatsoever. But people, I guess, are experimenting with these distinctions between short-term, very short-term risks, which then may be related to noise, and the more long-term cycle aspects. But then also you may have external factors which are not maybe related to cycles, like, for example, the governmental interventions within the COVID crisis. Maybe this would be then something that you need to tell the machine that there is some sort of structural break. You need to cope with this, I guess, in some sort of, how do we call this? Not artificial intelligence, but maybe augmented intelligence, where the human analyst needs to guide the AI through these structural changes, maybe.
That was going to be my follow-up question. That you know, often especially in a business context, someone will say, "Well, what happens if the Fed drops rates? You know, if interest rates go to whatever?" And so you've got a scenario-driven forecast that you need to generate. Have you seen any of the AI methods used in a scenario-driven context?
Not yet. And I'm also quite, so to say, humble in these areas. My forecast horizons are just about 1 day or 10 trading days within these techniques of market risk, since I know that forecast capabilities beyond maybe the 10 trading day is not too high, at least in the methods I encountered so far. And it has something, I guess, also to do with the inherent dynamism of financial markets.
Okay. Yeah, interesting. I guess in my own work, the only, you know, not very fancy, but we have done is to put in forward lags on some of the explanatory time series. So here you've got kind of a univariate problem that you're discussing, but where you've got multiple inputs, some of those inputs could be forward lags on some key variables that I then replace with a scenario, a prediction of the future. So you can train historically on a forward lag and then fill that in when it comes time to run a forecast. But in my experience, it's hard to get the model to pay enough attention because historically it kind of all looks the same. But when you're using it going forward, I'm really trying to tell it something it can't know.
So one
it's
aspect that
interesting.
so one aspect that is also resembles your thoughts, Joe, in this area is this forward-backward perspective, which I highlighted here on this slide, where on the lowest formula, the formula on the bottom of the page, you have this forward perspective applied coming up or applied based on historical experiences. So you look at the P&L from the next day based on the perspective of today. And then you say that something like this dynamism from one day to the next trading day would then somehow be in a certain way stable or predictable. This is the assumption here. So that may be what you had in mind. But as I said, making forecast horizons longer than a few days would maybe be a very interesting endeavor, so to say. And I haven't dared to embark on this endeavor at the moment.
I appreciate people sticking with us here. And does anyone else have any questions they'd like to ask?
Are there any experiences? Maybe I'm asking the audience. Any experiences with these techniques, which may be some sort of complement or even a contrarian view to what I have said, because maybe I just didn't look in the right directions concerning the applications of AI to time series analysis. So if there are any good ideas, please feel free to tell me.
Well, I will offer, Peter, that I think it's makes the problem easier that you're working on kind of daily timescales, so that you do have a lot of data. The realm I tend to work in is monthly data and looking through economic cycles, and we never have enough data. And so overfitting is kind of a given, that it's almost there's overfitting, and then there's, in a sense, not seeing some of the structure that we know must be there. And so things like the economic cycles, if I don't have data that goes back 12 years, and in most cases I don't, then what do I do with that? It would be like if I wanted to make a predictive model for something like SOFR, the new interest rate benchmarks, but they've only been around 2 years. So through an economic cycle, what do I do with that? And of course, there are some, you create proxies and various things. That's a rather trivial example, but I find these methods challenging to use where I need to look very long term, because there just isn't the kind of data that they've been designed for.
Yeah, that's true. So maybe one aspect that helps us with longer risk horizons would then be some sort of stylized fact that maybe, at least for the body of the distribution, you approximate a little bit your usual normal assumption, Maybe this is not the case for each and every time series, but there may be a tendency to do this. But yeah, you need to check this in each and every circumstance. There's another issue, because here I'm dealing with daily data. There may be another issue once you deal with high frequency data. Then there are, of course, there's much more data there, but you're dealing with other microstructure effects that are also very, very interesting to analyze within these machine learning or AI topics. So I tried to start these analysis, but since I don't have access to too many of these time series, somehow it stopped. But I guess there are a lot of microstructure effects once you're dealing with really high frequency data.
Yeah, and the experience I had there a long time ago, making models to predict currency futures, was that you get these structural effects, as you're saying, that are based on transaction cost. So there are these structure always exists right below the transaction cost threshold. And of course, if you have a way to change that transaction cost, then it changes the structure. But you don't want the model to just learn structure you can't trade, right?
Yeah, that's true. That's true.
In fact, in general, I think it's a problem I haven't seen addressed much, but often there's a dominant signal you can't use, and then a signal you're trying to find, or perhaps it's a transient signal, a very strong transient signal that's dominating the model, and you can't get it to ignore that and look for the more durable underlying signal. And so decomposing signals that way between the transient and the long term is an area I haven't seen addressed here, but it's I know it's important.
Yeah, but there are also, as I remember, also techniques. I mean, a lot of things related to the Kalman filter can also be found in this tradition of exponential smoothing. And there are libraries which try to apply exponential smoothing in order to filter out trends and also cyclical effects. So there is some sort of established way of doing this, but I think this is also due to the fact that in the 70s or 80s there was not much computing power, and those exponential smoothers were quite handy in these cases. But that is another different story.
Yeah.
Well,
Peter, thank you for your time today. I think you know, I won't try to clap, that never comes through well, but virtually I appreciate you making this presentation. This was very interesting. And we will make this available on our website. So
okay.
Thank you. Take care.
Okay, so thanks everybody for joining, and thank you for hosting the session. Okay, so thanks. Thank you. Bye.
Bye.